Okay, in this lecture we're going to talk about another theorem that helps us to find zeros. This is called the conjugate zero theorem because remember we had the fundamental theorem of algebra that said that any polynomial of degree 1 or more has at least one complex zero. So what if we do have a complex zero? So for example z equals a plus bi as a zero. Right, well we're going to use a fact about conjugates. You remember that when we talked about complex numbers, a conjugate was in fact the same number except for a different sign. And when we multiplied those two together, we actually ended up with a squared plus b squared, if you FOIL that out. And this, of course, is a real number. So we're going to use this fact that if I have a polynomial that only has real coefficients, and if I have a complex zero, a plus bi, right, where a and b are real numbers, then the conjugate, that's what this little bar up here means, which is a minus bi, is also a zero. Okay, and that's because of when you do the multiplication of the conjugates, we actually get a real number, and this is where the real coefficients actually come from. Now, conjugates have a few interesting properties. For example, so let's suppose for complex numbers c and d, all right, then if I have the sum of c and d, and I actually find the conjugate of the result, I'd get exactly the same result of getting the conjugate of c first and then adding the conjugate of d. Okay, it's not too hard to prove. You just have to put a plus bi in here and c plus di in here, add them together, take the conjugate, do the same here, take the conjugates first and add them up and you'll get the same thing. Similarly, if we do the product of two complex numbers and then take the conjugate, this is exactly the same as the conjugate of the products. Alright, and further we also have a power property which says that if I take the nth power of a complex number and then take the conjugate of it, right, same number, alright, different sign, then this is exactly the same as taking the conjugate first and then raising it to the power of n. Alright, so we keep these ideas of conjugates in mind, alright, but the most important thing to remember is that if I have real coefficients for the polynomial and I have a complex zero, then its conjugate is also a zero. So when it comes to a question like this, find a polynomial of least degree, alright, the smallest degree, having only real coefficients and zeros, -4 and 3 minus I. Now since I have real coefficients and I have a complex one, I know that 3 plus I is also a zero. So I really have 3 zeros, okay, and I can only have at most, and there's 3 different ones, and notice that I can only have a maximum of a degree n then because of our number of zeros theorem. So I want a polynomial, there might be several, but a polynomial of least degree with this would have the form f of x equals, of course, x plus 4, right, because this is our factor here, x plus 4, if -4 is a 0. Then we have x minus 3 subtract I, use the parentheses. And then, of course, we have x minus 3 plus I. Alright, and so this would be our polynomial. And, of course, this would be x plus 4. Now, what happens if I multiply this out? Well, I get x squared. I'm going to have negative 3 minus I x minus 3 plus I x, and then finally plus 3 minus I by 3 plus I. Alright, so that's what we have so far. So this will be x plus 4 by x squared. Now notice we have a negative 3x plus a ix minus a 3x again, minus an ix this time, plus, and when we do the product of conjugates, I'm going to get 3 squared plus 1 squared, because there's 1 in front of the i's. And if you FOIL this out, this is what you'll get. If you look at here, you get 9 plus 3i minus 3i minus I squared. These cancel. I have 9, subtract I squared is negative 1. So I end up with 9 plus 1, right, which is exactly what we have here. So this will be x plus 4 by x squared minus, that should be an x, minus 6x. This cancels with this, and I have plus 10. Now, of course, if I now multiply this, I'm going to get x cubed minus 6x squared plus 10x plus 4x squared minus 24x plus 40. So my final polynomial of degree 3, which is a degree of least, a polynomial of least degree, all right, having only real coefficients. If you look at this here, we have plus, so that would be negative 2x squared, and we have 10 minus 14x plus 40 would be my polynomial. Right, and so that's how we use the conjugate zeros theorem. Now the next one, we want to find all the zeros of this degree 4 polynomial, given that 1 plus I is a 0. Now you will notice here that I do have all real zeros again, all real coefficients again, and so consequently I know that 1 minus I is also a 0. Right, so now I'm going to use my synthetic division again, and we're going to have a 1 here, a negative 3 coefficient, a negative 8, a 22, and a negative 24. Now we have to be careful here because we're using a 1 plus I. We bring the 1 down and we get 1 plus I. Now we can only add real parts, so this would give me negative 2 plus I. Now of course I've got to multiply 1 plus I by negative 2 plus I. Now you'll notice that you'll get a negative 2. You'll get a 1i minus 2i's minus I. Right, and we'll have a positive I squared, which is negative 1, so I'll get negative 3 minus I. Alright, so this will be negative 3 minus I. Then when we add, we'll get a negative 11 minus I. And of course now we have to multiply this, so we're going to have 1 plus I again. This time we're going to do negative 11 minus I. Alright, so we're going to end up with negative 11 minus I minus 11I and minus I squared. So I'm going to have a negative 11, and this will be negative 1. Negative of negative 1 is positive 1, so this will be now negative 10. And we'll have subtract 12i. Right, so we put this in here, so it's negative 10. Alright, subtract 12i. And now when we add these, we'll get 12. And subtract 12i. Alright, now when we do this, of course, we're going to have to do the same thing again. 1 plus I by 12 minus 12i. So this is 12, subtract 12i, or plus 12i, that's interesting. And of course, minus 12i squared. So this will become plus 12 here, so this will be 24. And these cancel, so I'm going to have 24. And notice we get 0, so that verifies that this is in fact a 0. Alright, so now that we have that, okay, let me make a bit of space here. Alright, we can do the same thing again, except that now we have 1 minus I. So I'm going to do this here. I'm going to have a 1 minus I. I'll bring the 1 down, I'm going to have 1 minus I. Okay, now notice what happens here. When I add, I'll get a negative 1. When I multiply here, I'm going to get a negative 1 plus I. And when I add here, I'm going to have a negative 12. When I multiply here, I'm going to get a negative 12 plus 12i. And when I add here, I'm going to get 0, which verifies that this one here is a 0. Alright, so now what I have left is a x squared minus x minus 12. And of course we're looking for the zeros, okay? So I need to factor this, okay? So this will in fact be x by, we need a 4 and a 3 to get 12, so it'll be a negative 4 and a plus 3. And so all the zeros are going to be, so here's the zeros. Alright, we know that we have the given one, which is 1 plus I. We now have the conjugate, 1 minus I. And now when is this equal to 0? Well, this is going to be when it's negative 3 and when it's 4. And so now I have all the zeros of this degree 4 polynomial by using the conjugate zero theorem based on having just one zero, which is a complex zero. And then we get it finally down to a quadratic, and we can determine all of the possible zeros.